Hello, everyone. Thank you for your patience. I know we are getting started a little late, but we are trying to set up a way for us to share the fantastic new JWST images so that we can talk about those in real time. It is fantastic. We are very excited. Anyway, my name is Matthew, and I am one of the course instructors for our online classes. I'm going to hand this over to you, Chris, to start and welcome everyone, and then we will get started with questions. Please post those questions in the chat. I will grab them from there. Please ask only once. We see them. We just try to jump around and give a variety of people a chance to ask questions and hit a variety of topics.
Okay, welcome everyone on a very auspicious day in astronomy, as you all know, July 12th, 2022, the first science data release from the James Webb Space Telescope. So that'll obviously be a central focus of this session, but the floor is open for questions on any topic.
Excellent. So one of the first questions that we have, we will wait a few minutes to jump into JWST so that if other people are going to join us late, that they can get here. So we'll ask a couple of general questions, and then we'll hit those JWST ones. Hamid asks, can you talk about the different kinds of, or what kind of topology space-time has?
So it's an interesting question. In principle, space-time can have any kind of topology, very complex topology. The premise of space-time is based in general relativity, which says that the curvature of space-time, locally and globally, is caused by the density of mass energy, locally or globally. And so you can have, depending on the configuration of mass energy in the universe, or in particular astronomical objects, you can have quite interesting topologies. Now, what the universe actually has is a little simpler. It turns out that the large-scale structure of space-time is almost entirely flat. So no complex topology at all, described by Euclidean geometry, classical. But of course, in the regions of near-dense objects, such as black holes and neutron stars, space-time is highly curved and distorted, and light travels in paths and is gravitationally lensed. Now, a very interesting question in cosmology is whether there's a larger architecture of the universe where beyond the flat space-time we see to the edge of our horizon, or the edge of our view, the distance that light can have traveled in the age since the Big Bang, whether the space-time topology might be more complicated, whether we live inside a toroidal or a donut or a spherical geometry or a hyperbolic geometry. That's speculation. We have no observational basis for talking about that. But the theory, general relativity, does accommodate complex topologies of global space-time, the universe itself. And so, people can calculate these possibilities. It remains for observation to show whether any of them actually pertain to the universe we live in.
Excellent, thank you. The next question is from Ayush, who is on with us live. Does Moore's law stand for electronic devices that are already in space? Will it be possible to change semiconductor-based electronics used in space technology?
So space technology has benefited enormously from Moore's law. If we rewind to the Apollo program, fantastic technical achievement of the 1960s, that was really before, obviously, the personal computer. It was before microprocessor chips. And so there were no miniaturized electronics. There were still a lot of the hardware in the Apollo mission that was based on relays, really old-fashioned technology. So in the intervening half century, space missions have benefited from Moore's law, with one important caveat or limitation, which is that if for ground-based applications, we can have semiconductors coming out of labs and going straight into consumer devices. When you launch something into space, it has to be flight tested, it has to be proven to withstand the rigors of zero gravity and high cosmic ray incidence and vibration and shaking when it's launched. So the stresses on electronics that are destined for space are much higher than the stresses on consumer electronics. And that means there's a lead time. So typically for typical instruments like those in the James Webb Space Telescope or the Hubble Space Telescope, their designs have to be frozen. The hardware essentially has to be locked down several years before launch, 3 or 4 years even. And that means you're always launching into space, whether it's a planetary probe or a space telescope, hardware that's sort of 3 or 4 years obsolete or behind the time. So you never benefit from the very cutting edge technology that you might use on the ground. That's just a limitation of working in space environment, which is very unforgiving. But overall, Moore's law has benefited enormously what happens in space, and the best example of that are the miniaturization of CubeSats and tiny robotic spacecraft that we're now designing to travel around the solar system powered by solar sails. So Moore's law has absolutely been an enormous boon to space exploration using robots.
Excellent. The next question is from one of our online participants, and it is, let's see, can you say something about the hyperfine transition of the hydrogen atom in nebulae? This is from Bismarck G. Oliveira.
Mm-hmm. So nebulae typically have very low temperatures, so the densities and temperatures of the gas in a nebula, unless it's very near a hot star that's ionizing the nebula, tend to be very cold. Temperatures of 10 to 30 to maybe 50 degrees Kelvin above absolute zero. And at those low temperatures, we see different kinds of spectral transitions of atoms and molecules than you typically see in hot regions. And the hyperfine transition of hydrogen as a sort of fundamental one only occurs in very low temperature regions. And it's a very important diagnostic of those kind of cold gases. And so it's used in spectroscopy and astronomy, used at millimeter and radio wavelengths because these are very low energy transitions to diagnose the physical conditions inside nebulae, and that's almost a unique diagnostic.
Excellent. The next question, just 1 second here. Sorry, like I said, I'm kind of jumping back and forth between a few things here. The next one is from Kendra Smith, who would like to know, how did the Oort cloud originate?
Well, we really only have speculation about the Oort cloud. First of all, we only have indirect evidence that the Oort cloud exists. The Oort cloud is the parent cloud of the comets that we see coming into the solar system on orbits that take them within the realm of the planets. And we know from their highly elliptical orbits that these comets that we see in the solar system must spend an enormous amount of their time, due to Kepler's law, at very far reaches from the Earth, because they're very highly elliptical orbits. And so it's hypothesized that the parent cloud, if you like, of the comet population that we can see in the solar system is an enormous number of cold comets, cold because they're so far from the sun, that live at distances of hundreds to 1,000 astronomical units. And the size of this cloud is obviously much bigger than the planets in the solar system, and the number of comets is just inferred to be a very large number, perhaps 1 trillion. So we don't actually directly observe this parent cloud because it's too far away and the objects are too small and dark. How it formed is that it probably formed in the solar nebula collapse, and this comet cloud is essentially a relic of the full extent of the nebula that formed the sun and the planets. That nebula collapsed, and it collapsed in rotation to form a disk, and the disk formed planets, but that contraction of the disk was by a large factor from the original size of the nebula. So the comet cloud is a sort of frozen relic of the original size of the nebula, where there were condensations formed by gravity that formed small objects like comets, and those comets persist to the present day on their highly elliptical orbits.
Excellent. Thank you very much. American Utility would like to know, how do they define up and down in space?
Well, it's not necessarily defined in space, because as soon as you're in a zero gravity environment, there's no reference for up or down. On the Earth, up and down is defined by local gravity, which of course means that what's down for us is up for someone in Australia. So even up and down on the Earth is a relative concept because the gravity all points to the center of the Earth. In space, up and down really doesn't have a meaning. It's all based on local gravity. Now when you're in a rocket ship that's being accelerated, then that force acts very similarly to gravity, and so you can imagine what would be down for a spaceship. If we ever develop colonies in space, it's assumed that there'll be large wheels that will be rotating to create artificial gravity. So down for people living in these space colonies will be radial vectors pointing outwards, like the spokes of a wheel, towards the outer perimeter of their cylindrical habitat. So down is a fungible concept in space.
Excellent. The next question is from DS, who would like to know, when calculating the gravitational effects between two objects in space, do astronomers use Newton's law or Einstein's law, or both?
You can use both or either. Einstein's law and Einstein's theory of general relativity is the superior theory of gravity because it applies in a larger range of physical situations. But when you're just calculating the gravity between two objects, Newton's law is exact and works very well. However, if those objects are very dense and compact like black holes or neutron stars, you still need to use general relativity because of the curvature of space-time. But just in general, if those two objects are, say, stars, normal stars, or planets, or spacecraft, or asteroids, or any small object, Newton's law works perfectly well. And so most simple calculations of gravity in space are still done using Newton's laws.
All right, the next question is from another one of our live participants. Lamont Lathan asks, how likely is it that there is another force in the universe affecting the motion of the planets besides the ones we already know?
Well, the idea of a fifth force, or a force beyond the four that we've known about for decades, is a persistent idea. It hasn't completely gone away. So the forces that we know of in the universe in decreasing order of strength are the strong nuclear force that holds the atomic nucleus together, the weak nuclear force responsible for radioactivity, the electromagnetic force responsible for the radiation we see, including light in the universe, and gravity itself, by far the weakest force. Now, the fact that we're inferring dark matter in the universe has led some people to speculate that perhaps there is a fifth force, or at least a variation in the fourth force beyond what we've always understood to be an inverse square law. And so the inference of dark matter has led some people to speculate about an additional force of nature. But there's no particular way using current data to tease out what kind of force that might be. In physics, there's also possible speculation, that has happened for the last few decades. There might be additional forces of nature. But again, there's no experimental evidence for any force beyond the four that we currently understand.
All right, so we are well into it now. We have a lot of viewers. I think we're going to get started with the James Webb questions. I've kind of combined all of these together. So we'll essentially convert this session now to a James Webb Space Telescope Q&A session. If we run out of James Webb questions, we can go back to regular ones. But since that's such, breaking news, there's a lot of discussion to be had. I will ask a question and we can switch over to the pictures as necessary. I do have to, I made one mistake when I was setting up the image presentation slides. There's no audio on those. So as soon as we switch over, there's going to be a short hiccup where I have to add the audio sources in to that screen, and then you'll be able to hear us. But when we switch over to those videos, I will let you know that there will be a short pause, and then I'll add the audio sources, just so that you all are not surprised that there's a short pause when we switch over to that. But first, let's talk about some of these like more general questions. Prabir Ahadikari asks, can JWST change or shift the theory of the Big Bang? What are your ideas?
The James Webb Space Telescope is not particularly designed to test the Big Bang theory. The Big Bang theory has affirmation from lots of evidence, but primarily microwave background at this point and redshifts of galaxies. James Webb is not really situated to test the Big Bang in any particular new way. What it's going to do is fill in some of the picture of the Big Bang, which is to take the time period from the microwave background radiation formation, which is 400,000 years after the Big Bang, to the very first epoch of stars and galaxies, which is roughly 500 million years after the Big Bang. The James Webb is going to fill in the early story of the Big Bang.
Excellent. Can you give us a little lead into the images? Can you talk about what James Webb is and what we're about to see?
So the general statements I can make about the James Webb Space Telescope is that it's a highly anticipated facility that astronomers have been planning for decades, literally decades, 25 years ago when the project formally kicked off. It's conceptually, you can think of it as a successor to the Hubble Space Telescope, which is now over 30 years old and showing its age, and eventually the Hubble Space Telescope will die because it'll lose enough gyros that it simply can't point anywhere. And so it's a successor in the sense that it's larger, 6.5 meter telescope. That's 8 times the collecting area of the Hubble. It's also shifting its focus to the infrared rather than the visible, which is deliberate because the science it's doing is preferentially in the infrared wavelengths. It's not in Earth orbit. It's at 1 million miles from the Earth in a very safe and dark and quiet place for doing infrared observations. And it's also an extraordinarily complex, sophisticated observatory, probably the hardest thing NASA's ever done. Also the most expensive thing NASA's ever done. I think the price tag at the time of launch was about $11 billion. It's had a rocky road to launch. It's had a rocky road to prepare these instruments and get them all checked out. Its budget overruns have incurred the wrath of Congress occasionally and taken it very close to cancellation several times. But it persisted. Launch came just before Christmas last year, and now 6 or 7 months later we're seeing the first science images.
Excellent. So the first image, should we talk about the first image that was released, the wide field view or the deep field view, or should we
do them in whatever order? I don't mind.
Okay, sounds good. So the first image that we're going to talk about is the first one on their website, which is the Carina, the star forming region Carina image. So I'm going to switch over to that. There will be a quick pause while I add your audio, and then you can just start talking about the image, and I'll pop in some questions that are related that have come up on the in the chat. So here we go, that switch over.
So we're looking at the first image in the way that NASA presented it on their website from the early science data release from the James Webb Space Telescope. And the release date of all of these first 5 images was July 12th, 2022. This is an image of the Carina Nebula. Now, actually, in the live press conference, this image they saved till last because they considered it the most spectacular, and it is indeed a spectacular image. This is the Carina Nebula. If you go to the Hubble Space Telescope website, you can also see gorgeous images taken by the Hubble Space Telescope. And so there's a counterpoint here between what Hubble saw working at visible wavelengths and what James Webb sees working at infrared wavelengths. The Carina Nebula is a region of star formation, current active star formation, 7,600 light years from the Earth. And the colors and the textures, the bubbles, the jets, the extraordinary features you see in great detail, showing the optical quality of this telescope, this new telescope, the James Webb, it's a rich landscape for understanding star formation. And the colors here are, of course, false colors because we're looking essentially at invisible mid-infrared wavelengths, things you can't see with your eye. And so essentially they've taken the shortest of those mid-infrared wavelengths and turned those into blue filters, and then the longest of those mid-infrared wavelengths and turned them into red. And so they've made a blue, red, and a green mapping of mid-infrared into visible, and then combined those into what is a true color image. But remember, we're still looking at radiation that your eye could not detect. And the details and the textures are going to keep astronomers busy for quite some time.
Excellent. The next image that we are going to see is the Stephens Quintet.
So this image from the first early science data release from the James Webb Space Telescope is a very well-known group of galaxies. It's been known to extragalactic astronomers for 70 or 80 years, called Stephens Quintet. You're seeing 5 galaxies. The galaxy at the left is a foreground galaxy. It's not at the same distance as the other 4. The other 4 on the right, running up and down vertically, are all at the same distance of about 300 million light years from the Earth. And those galaxies are all in one region of space, and they're clearly interacting. And so we see the interaction between these galaxies happening in real time. Some subsequently, millions of years from now, a couple of those galaxies will probably merge, but we're watching a sort of slow motion train wreck or a collision or interaction between 4 galaxies, creating interesting features, triggering star formation. There's a lot of details here. And in the galaxy at the top, the infrared observations have penetrated the gas and dust and shown that there's a black hole in that top galaxy that has a luminosity of about 40 billion times the luminosity of the Sun.
The next image is the side-by-side of the stellar death ring of the Southern Ring Nebula, I believe is what this one is called.
Yes, so this image from the first early science data release from James Webb Space Telescope is called the Southern Ring. It's a planetary nebula. Planetary nebula is a late stage of the evolution of stars like the Sun. The Sun will go through this phase at some point in its life before it turns into a red giant and then dies as a white dwarf. It represents, as you can see, the ejection of gas. So stars like this, late in their life, actually eject something like a third to maybe a half of their mass in hot, glowing gas that punches out through interstellar space and is still heated by the star and so glows brightly. And so the ring, the shells, the foamy textures you see are all caused by interactions between this outflowing gas, the star that's irradiating the gas at the center, and the medium that this gas is traveling out into, the sort of interstellar medium. The 2 images are a near-infrared image. These are taken with different instruments among the James Webb instruments. On the left, you're looking at a near-infrared image, which is good at showing the sort of hot stars and the hotter material at temperatures of hundreds of Kelvin. And on the right, you're seeing the mid-infrared image, which is better at penetrating through all the dust and tends to look at the cooler material with temperatures of 30 to 50 Kelvin. So these images sort of complement each other, and they show different aspects of this planetary nebula. And the surprise, on the image on the right in the mid-infrared, which penetrates all the dust, is that there's a binary star, and you can see the binary very clearly at the center of the galaxy. And that really was a surprise to the astronomers who took this image.
The next image is of an exoplanet, and Brenda commented, "Hello, I just watched the first images from the JWST and was particularly pleased to see transit data as we learned about it in the astrobiology class. Can you talk about this image, and how do they know from the transit that there was water?"
So this is the only image that's not really an image. This is a graph. It's a spectrum. So James Webb Space Telescope has different types of instruments. It has imaging instruments and spectroscopic instruments. And the information you get from a spectrum is a little different from the information you get from an image. This is a hot gas giant exoplanet, WASP 96b. It's about 1,000 light years from the Earth. And it's actually very similar in properties to the very first exoplanet ever discovered, 51 Peg, in 1995, because this planet also has a mass about half that of Jupiter and an incredibly rapid orbit around its sun-like star, 3.5 days. These are both very similar quantities to 51 Peg. So you can think of it as sort of a twin of the very first exoplanet. It's a hot gas giant, not any kind of object we would ever expect life or biology to be on. So this observation of the transit is sort of a proof of concept for what eventually will be the exciting work of trying to look for life by the atmospheric alteration of an Earth-like planet. Oxygen is the biomarker, because in our atmosphere it indicates microbes existed on the Earth and still exist, and that's how we do it on exoplanets. This is not an exoplanet where we expect to find oxygen or those signatures. So you take the situation where the planet passes in front of the star every 3.5 days, and you take a spectrum, and what you see is that the light from the star filters through the gas, through the atmosphere of the star, and imprints through absorption lines, which are the bumps and wiggles in this graph, imprints that on top of the light. And so it's the variations, these absorption lines or bumps and wiggles, that can indicate the chemical composition of the atmosphere of this hot planet. And you've seen marked on this water. And so it's very clear that there's water in the atmosphere of this exoplanet. Now, it's a hot enough planet that this water is actually steam. It's in the vapor state. So this is a proof of concept, because having water vapor in the atmosphere of a hot exoplanet does not tell you that there could be life there or there is life there. But eventually, when this type of data gets done on much lower mass planets that are more Earth-like, then we have a very interesting experiment to potentially look for life on another planet.
All right, and the final image for today is this deep field image that was the first one released. And can you talk a little bit about what we're seeing in this?
Yes, this is the deep field. It's not a random point in the sky. The point was made in the press conference this morning that there's no blank piece of the sky for James Webb. It's so sensitive that anywhere you point the instruments, they will detect galaxies. And so you could point it at a random area of sky and you would find hundreds of galaxies littering the frame. In this case, a particular target was chosen. The bright and tending to be white or yellowish galaxies in the center of the image are a cluster of galaxies about 4.5 billion light years away. So the light from these galaxies has been traveling since the Earth formed. So that cluster is the foreground object, and then the arcs you can see galaxies light, which is typically reddish, that form slightly distorted fractions of a circle, or arcs. And if you look carefully, those arcs tend to be concentric about the center of the image, which is the mass of the cluster. This is Einstein's theory of relativity predicting that mass bends light, and so the cluster at 4.5 billion light years away is bending the light from much more distant galaxies and stretching that light into little arcs, and also magnifying it. Just like a lens magnifies light, a gravitational lens magnifies light from a background galaxy. So when you have a lens situation like this, it's like you're using the universe as a telescope, and you're magnifying galaxies that are very, very far away to a brightness that lets you see them where you otherwise might not. It's known that the most distant galaxies in this frame are over 13 billion years old. The universe is only 13.8 billion years old, so these are galaxies really in the very first fraction of the age of the universe. It's a very exciting image.
Excellent. All right, so now we'll hit some questions that we have about these images. So HGE Rector, who's on with us live, asks, in the JWST images, are the 8 flares around the brighter stars artifacts of the telescope structure? Can or should they be removed in post-processing?
So when you see stars in these very deep images, they're foreground stars. So mostly James Webb is looking at galaxies, as in the deep field, but you do see some bright stars in pretty much any image. These are foreground. These are probably stars a few hundred light years away in our own galaxy. They are so bright that they saturate the detector, and they are so bright that they create diffraction spikes. That's just a standard optical effect from any unresolved point source reflecting the optics. It's an inevitable outcome of optics working at its diffraction limit. Now in this case, you can model the diffraction spikes because you have an optical model for the telescope light path, and so you could model them and subtract them out and remove that bright star pretty well. And for cosmetic purposes, sometimes people do, but mostly they just work around the bright stars because there are not very many of
them. That leads us nicely into a question from Demetrius, who asks, let's see, are all of these spectacular images just a composition of different wavelengths, green, blue, red, or are they aesthetically adjusted to provide us more information?
They are aesthetically adjusted, in fact. That's a good question. One of the project scientists at the press conference pointed out that the business of making these color images from a space telescope is as much an art as a science. So I rewind to my original point that we're looking at invisible radiation. So this is not what these regions of space look like because we can't see them with our eyes. The telescope is working at wavelengths longer than the eye can detect. So we are essentially mapping the shorter wavelengths, the shorter invisible infrared wavelengths, to blue colors in light, visible light, and the longer infrared wavelengths to red colors in visible light, and then juggling the various colors, red, green, and blue typically, to make a true color image. And there's a lot of free choice in how you do that. You can weight the different intensities of those 3 channels differently. And since you're not dealing with the way it actually looks to your eye anyway, you have some artistic license to do that. So people tend to do this color mapping in a way that produces a good aesthetic outcome, which is to say the colors look natural. You see a full color range across the color table from the bluest blue to the reddest red, and hopefully you can accentuate some of the features and the fine details in the image. So all those things go into making these color images, and it's quite a lot of work actually.
So P51 has a couple of relevant questions here. So we know that these images are false color. How does James Webb in particular create these false colors? Does it have filters that detect slightly different wavelengths of infrared? Does it have totally different detectors that are then combined and each color adjusted independently? Or are the colors all just the same and they've sort of faked the blues and reds?
There's different parts of this. Let me unpack it a little bit. Essentially, for the astronomy, for the astrophysics, for the research of this, making a visible image is sort of irrelevant. Making a pretty image, a pretty picture that you can put on the web is not really what it's all about. In the end, it's about measuring the radiation and understanding what that radiation is telling you, what the different proportions of the mid and the short mid infrared wavelengths and the long infrared wavelengths are telling you. And you can understand that image and the science of it without ever making a picture, in a visible picture. So it's really something that's done for other purposes, essentially for aesthetic purposes, for public relations or publicity or outreach or education. So the data is the data. These are digital, these are detectors that are detecting photons at different wavelengths, and that is converted into an intensity, and those intensities can be manipulated and modeled, and you can calculate all sorts of things without ever making the image, right? So that's the first point. The second point is that when you do want to make a visible image, you're dealing with invisible radiation. So it's arbitrary and artificial immediately, right out the gate. It's arbitrary or artificial. So obviously choices have to be made, and different people might make different choices. And in fact, there are tools available, and Hubble Space Telescope had these tools too, and has been doing this for decades, that would allow, you know, an amateur astronomer or someone with a little technical background to take the raw data and make their own optical image and do their own false color mapping. So these are choices that anyone can make, not just astronomers. So that's the second point. And then the third point is, the real question is, you know, do you want to, what's the best way of getting the information out of the image? And like I said, you don't have to make an optical image of infrared data to get the science out of it. And so the optical image is really sort of serving a different purpose. It's visualizing what the James Webb is seeing. It's giving us an aesthetic sense of the beauty of the night sky. And it's also helping us explain why it was worth spending so much money on this telescope.
We have another couple of questions that are related to each other. So one is, are any of the colors that we're seeing in this image, I'm assuming that we'll talk about, I'll bring it back up in just a second, the deep field image, are any of the colors related to redshift when we see very distant galaxies?
Yes, the colors are indeed related to redshift, with the caveat that once you've mapped into an optical color, you've changed the wavelength essentially. You've taken the wavelength from an infrared wavelength to a much shorter wavelength, just so you can make an image that human eyes can see. So you've altered the data. But in their original form, the different wavelengths of infrared radiation from galaxies are absolutely related to redshift, because galaxies have an energy distribution, and that energy distribution has a particular shape. And so when you observe a galaxy through a fixed set of filters at fixed wavelengths in the infrared, that galaxy, as the galaxy is higher and higher redshift, shifts through those filter bands, and so the colors actually change. And so the infrared colors in the real data from James Webb absolutely are telling us something to do with redshift, and actually allowing us to estimate redshift without taking a full spectrum. So those colors are actually very valuable. And part of the point of James Webb is that when a galaxy is very high redshift of 8 or 10, which means the universe was 10 times smaller when that light was emitted than it is now, then there's almost no optical radiation from those galaxies. It's all been redshifted to longer wavelengths. And so a telescope like Hubble really would see very little or nothing. And that's why these galaxies, many of them, would be undetectable with the Hubble Space Telescope, apart from the fact that it's also a smaller telescope. So there is a point in redshift and distance and look-back time where James Webb is the only game in town.
Excellent. The next question is also about the deep field image. And the question is from Rajarshi Roy, who asks, how far back in time is this new picture by JWST? I think you answered it a little bit earlier, but let's
Sure. So the bright galaxy cluster in the center, which is acting as the lens, is 4.5 billion light years away. And so that's about a third of the age of the universe back, look back time of 4.5 billion years. The faintest galaxies, apparently, according to the science team, are about 13.1, maybe 13.2 billion light years away. The universe is 13.8 billion years old. So these are galaxies seen within about 500 million years of the Big Bang itself. That's in the very first phase of galaxy evolution. Now, James Webb, one of its goals is to detect the very first light, that is the oldest light in the universe, the very first galaxies. Now, these galaxies are not there yet. There are probably galaxies you can find that are redshift of 13.5 billion years old, within a few 100 million years of the Big Bang, and we haven't seen those yet, but it's certainly heading in that direction.
The next question is from Faisal, who asks, After displaying images taken by JWST, are the images of distant galaxies that appear distorted and stretched due to the gravitational lensing, can they be, I guess I'm not sure she's asked, she says, can they be technically more clear and accurate? I'm not sure if she means, are they clear enough to tell something about those galaxies, or if we can clean up the image so we can see those galaxies behind the lensed galaxies more clearly.
Yes, you can actually. So you're looking at a gravitational optics experiment where you see where the lens is traced by those bright galaxies in that cluster at the center, and where the distant objects at the far end of the optics experiment are those little arcs whose light has traveled, been deflected through some angle, as in a lens, and magnified. And so yes, once you know what the lensing geometry is, once you know what the mass of the cluster is, you can make a model for the lens, and you can reconstruct the object, those objects that have been stretched and distorted in the image. You can reconstruct what they look like before, without the lens in place. So yes, you can, in that sense, you can clean them up entirely by calculating using a lensing model what they look like if they were unlensed, what their true shape and color is.
The next question is about the Stevens Quintet, Stephan's Quintet. I'm not sure which one it is.
Yeah.
Stephan's, okay. Stephan's Quintet from Röntgen 101. Stephan's Quintet seems to show that galaxies are ripping each other apart and stretching space-time along which mass seems to be moving differently. Is that possibly what's going on in there?
It's not a very big distortion of space-time. So these are not highly compact objects like black holes. So the overall distortion of space-time in this region of space where you see these interacting galaxies is very mild. I mean, they are gravitational potentials, so there's some mild distortion of space-time near the center of the galaxies. But what we're seeing is not a reflection of distorted space-time. What we're seeing is a reflection of gravitational interaction. Remember, gravity is a long-range force that goes as the inverse square of the distance. So when two galaxies interact, their near and far regions interact obviously less strong in the far region, but gravity has an infinite reach. And so as galaxies interact, they don't have to actually fully merge or pass through each other. They could just be orbiting in a tight orbit around each other. Those gravitational interactions will fling out long arms. So when you see the arm that's going off to the top of that image out from that top galaxy, that's an arm of stars that have been flung off by the gravitational interaction with a partner. And again, we can use computers to model these interactions and produce very similar pictures. I mean, not maybe exactly reproducing this image, but show how clearly galaxies get distorted and warped and have arms of stars flung off and streamers and trails of stars and areas of star formation triggered, as you see near the center of this image. So all of these things are well understood in terms of simple gravitational interactions.
The next question is from Pablo, who's on with us live. And we answered this a little bit with one of the images, because this was asked before we talked about the images. But perhaps we can get some more detail. Now that the JWST is fully working, it will be investigating exoplanet atmospheres. Could you give me an example of a substance that you would consider rare and that you would attribute to life?
So in terms of its exoplanet observations, James Webb is an important caveat to say up front. James Webb was conceived before the first exoplanet was discovered. It's been that long a project, in other words, before 1995. And so James Webb was never designed to study exoplanets. And the truth is, it's not optimized to study exoplanets. It was really built to measure first light in the universe. It was a cosmology telescope, large part. Of course, exoplanets are exciting enough, and James Webb has sufficient capabilities that it will play a part in exoplanet studies. But it's not the best tool. It's actually going to be pretty hard to do work with James Webb, despite its size and sensitivity. And that's partly because its spectroscopic capabilities are fairly limited. There's a limited range of wavelengths that it can observe, and a limited resolution and sensitivity for infrared spectra. And so you have to essentially be opportunistic. You have to hope for spectral tracers that happen to fit in the windows of wavelength you have available to you. And in this sense, oxygen, which is the classic biomarker for life perhaps on a terrestrial planet, is not presenting, it doesn't present any strong spectral features in the range that James Webb is sensitive to. There's actually a very strong ozone feature at about 10 microns that's not in the James Webb range either. So it's just bad luck, but again, it wasn't designed to do this, that oxygen and ozone are not going to be in the wavelength range for James Webb. Probably the best biomarker for James Webb is going to be methane. So there are methane bands that will appear, and so it will be looking for methane and also water vapor, as we've seen in this first giant planet, this hot giant planet. Methane is a good biomarker. It, of course, can be created abiologically or geologically on the Earth, but a lot of the methane on the Earth comes from cows and ruminating animals and so on. And it's a greenhouse gas. So I think methane is perhaps the singular target that James Webb will be looking at when it gets down to looking at super-Earth planets.
Next question is from Raul Gonzalez. Can you compare and contrast the James Webb telescope with some of the upcoming extremely large telescopes that will be coming online? For example, the 30-meter telescope, or the GMT, or the ELT?
Sure. So James Webb is by far the largest, most complex, and most powerful space observatory ever built. That's a strong statement, period, end of sentence, right? However, it's not the largest telescope even now on the Earth. There are 10, 12-meter telescopes on the ground. And as you know, there's a series of 20 to 30-meter telescopes currently under construction. So there are telescopes on the ground that will have an order of magnitude more light gathering power than the James Webb. And for doing some difficult experiments like Earth-like exoplanets, extremely distant galaxies, and so on, there's no substitute for gathering photons and more light. Generally, the space environment is better for sharp observations because there's no atmosphere. You can be diffraction limited. But on the Earth and in these large new telescopes, adaptive optics is promising to give these big new optical telescopes diffraction limited images. So their images should be just as sharp as James Webb, and in fact a little sharper because they'll be working at visible wavelengths rather than infrared wavelengths. So for some experiments that the James Webb is going to do, particularly in the exoplanet regime, the ground-based telescopes have more capabilities and probably will generate more science.
The next question is from Parth Sarda, who asks, how will JWST filter out or avoid the interstitial disturbances within our galaxy, like the dust and gas around the Kuiper belt and external obstructions, which can cause problems or changes in measurements?
So James Webb is not given free rein to look anywhere in the sky. It obviously has, because it's so sensitive, it has to avoid anything looking, even though it's very far from the Earth, it has to avoid Earth shine. So looking anywhere within 30 or 40 degrees of the direction of the Earth. Obviously it has to avoid looking at a large angle from where the sun happens to be at that point in its orbit. So it has to avoid that, and it also just tends to avoid the region of the heaviest zodiacal light. So when it's making the most sensitive observations, such as these deep field observations where you invest a lot of time looking deep in one direction, then yes, you have to avoid regions where you know there's a lot of local dust in the solar system, or regions where there's a lot of glow, those directions in the sky, or even the galactic plane. So you look at high galactic latitudes, you're looking directly out of the galaxy where there's less gas and dust. So James Webb will be cognizant of all these different limitations on where it looks. And so although its target list is extensive, it's highly pruned and modulated by the ability to look really deep in really clear and clean directions in the sky.
Patricia asks, how is it possible to identify, or is it possible to identify the effects of dark matter and dark energy in the first picture from JWST? I'm assuming she's referring to this one, the wide field,
Right.
deep field. I mean,
So an image like this is a very, very good way of diagnosing dark matter, the distribution of dark matter. The key here is that in the theory of gravitational lensing, mass bends light, and it's any mass that bends light. And so if you make a model of the gravitational lensing in this image, which is fairly easy to do, we've been making these models for decades now, because we've had images like this at visible wavelengths since Hubble was launched, so it's 30 or 40 years now. When you make a model, the gravitational deflection of those background galaxies, the angular deflection and the magnification, are telling you how much mass is in that cluster at different radii. And it's all the mass. It's not just the visible stuff in the galaxies we see in front of us. It's the dark matter too. So the lensing model gives you a dark matter map of this cluster. So it's actually one of the very best methods we have for looking at dark matter, and it's affirmed in many cases, in hundreds of examples like this, that there's 6 or 7 times as much dark matter as visible matter. This type of observation is not as directly useful for measuring dark energy. For dark energy, you need to look at larger volumes of space and compare different redshifts and do different kind of survey.
So in a related question, Parth Sarda asks, how will JWST enable us to get a better understanding on the formation of galaxies and among galaxy formation? And how does dark matter play a role in galaxy formation? And can this help us with observations of dark matter for galaxy formation?
Well, James Webb, through these deep surveys, this is just the beginning. Remember that the data we've seen in the first science release is based on less than 5 days of observation. James Webb is going to be up there, we hope, for about 20 years. So you're looking at less than 0.1% of all the data that it will produce. This is just the first taste. In those deep surveys taken together, we should be able to piece together the story of how the first galaxies formed and when. From within 100 million years of the Big Bang to about 500 million or 700 million years after the Big Bang, when the story is picked up by Hubble, and we've told that story pretty well. And that formation scenario, which involves mergers, because galaxies grew by merging, combined with these lensing data, will actually allow us to show how the dark matter contributed to the way galaxies grew and merged. So we think that galaxies are surrounded, they're all embedded in dark matter halos, and when galaxies merge, their dark matter halos merge too and grow. And so this will be hopefully a consistent story that James Webb is able to tell when it's finished doing its deep surveys.
The next question is from Vivek Kashyap, who asks, since these colors are not visible to the human eye, what would be the closest real, quote, colors of these images if we remove the artistic liberty? What are the true colors?
Well, it's sort of it's a non sequitur question, unfortunately, because we can't talk about a true color for invisible wavelengths of light. We refer to color and we reference it to visible light. And so our sense of the colors of the rainbow and the colors of the visible spectrum are completely tethered to our sensory equipment of eyes. We are unable to see infrared radiation. Now there are animals. Animal kingdom includes creatures. There are some creatures in the ocean that have infrared sensing eyes. And so not the ones in the ocean, but perhaps some of those other creatures could stare at infrared data from the universe and see it naturally. But there's no way to call an infrared color and to refer to it as a true color. It's automatically and necessarily a false color as soon as you take it into the visible regime.
The next question is from Andronash Adriana Valentina. If to see further in space, we need telescopes that can see longer wavelengths, such as James Webb that can see further than Hubble, what are the drawbacks of space telescopes in even longer wavelengths like microwave or radio?
So telescopes do the thing they're designed for and have particular purposes. James Webb is an optimized near-infrared and mid-infrared telescope, and it's about as sensitive to those type of wavelengths as you can possibly imagine. The limitation when you go to longer wavelengths is due to the wave nature of light. So the diffraction limit, in other words, the sharpness or the resolution of any image, is not just a function of how well you build your instrument, it's a function of the wavelength of radiation you're looking at. And the diffraction limit scales with wavelengths. So the diffraction limit at 2 microns in the near infrared is 2 times larger than the edge of the visible spectrum, just under 1 micron. So images are 2 times less sharp intrinsically, just because of the wave nature of light, not a limitation of the instrument or the detector. And so as you move from near infrared to mid infrared, the diffraction limit grows, and so your resolution or sharpness degrades, and you just can't see the fine features you might hope to. As you take that further towards microwave or radio wavelengths, you're going factors of hundreds or thousands of times longer wavelengths still. And so an image which at a visible wavelength might have a resolution of 1 arc second starts to have a resolution of multiple arc minutes. And so we get the microwave background maps we've made of the entire sky, where the resolution is significant fractions of a degree. And so that's really the main limitation that arises from observing at longer wavelengths. It's not really about sensitivity anymore, it's about resolution.
P51, who's on with us live, asks, what is the big difference between the WM Keck infrared telescope and JWST?
Well, the Keck telescope has infrared instruments, as do all the major optical telescopes, our Large Binocular Telescope, the Magellan telescopes in Chile, ones that I've used here in Arizona. All major observatories have infrared telescopes. The real difference and limitation is that from the ground, only certain windows of electromagnetic radiation reach the Earth's surface. So, and that's basically because of water vapor. So water vapor in the atmosphere interacts strongly with long waves of light, and essentially the atmosphere becomes opaque beyond a certain wavelength. So the visible spectrum, the one we see with our eyes, is a nice transmissible clear window through the atmosphere, and that radiation comes directly to us. And then there are a few small windows in the near infrared, which we use and have used for 50 years to make infrared data from Keck and other ground-based telescopes. And those windows are around 2 microns, 3 microns, 5 microns, and then going into the mid-infrared, 10 microns. There's a very bad kind of soggy window, because there's still water vapor, at 20 microns, and that's it. So from the ground, there's only certain windows accessible for observations through the atmosphere at near and a few mid-infrared wavelengths. The atmosphere is really opaque for most of the mid-infrared. And the contrast is dramatic, because with James Webb, there's no water vapor. You're not dealing with any atmosphere, and so all wavelengths come with equal efficiency to the James Webb, and they're detected just according to the sensitivity of the detectors.
The next question is from Kevin Sharma, who asks, the JWST is intended to capture some of the first light from the universe. Could you shed some light on why understanding first light and the early conditions of the universe are of such high importance?
So it's a good question, because it's not fundamental to our cosmological model. In other words, the detection and the understanding of first light in the universe is not foundational to whether or not we believe the Big Bang theory. The Big Bang theory rests or will rest or fail based on other types of evidence. It's within the context of the Big Bang theory that we want to understand when the first structures formed in the universe. Remember, the universe started completely smooth. The microwave background radiation is telling us that the universe was smooth to 1 part in 10 to the 5, 400,000 years after the Big Bang. That is to say, there were no ripples in either matter or radiation more than about 1,000th of a percent. Somehow, over time, through gravitational instability and just slow gravitational amplification, the first structures formed. And that process is very interesting. Did it happen quickly? Did it happen in an accelerated way, so that we had stars, small things forming before big things, stars before galaxies? When in this sequence did black holes form? Because we know black holes are left behind when massive stars die after the first generation of stars, but they're also at the center of every galaxy. So did the black holes form first and then galaxies nucleate around them? Or did the small galaxies form first and they grew black holes in their centers? James Webb is going to help answer all of these questions and just play out this whole landscape of stars, galaxies, black holes, and how they co-evolved in the first 500 million years after the Big Bang.
Astro Guy would like to know, is there any possibility that the light captured by JWST was somehow reflected before the light from those galaxies hit JWST? Basically, like, I think they mean, is there any stray light, that JWST could be picking up from other sources?
So the optical quality and optical design of JWST is designed, as with any major telescope, to minimize stray light. Because it's true, there are places where stray light can come, or light that can scatter off the telescope assembly itself. Remember, it's not just a primary mirror sitting out there in space, which in James Webb is a segmented primary mirror. It has a structure that holds it in place, and so there's essentially metal scaffolding, and light can scatter off those. So there are ways there can be stray light in any telescope, and you essentially have to know the optical design and the optical path, and you have to model this very carefully. And you can minimize it by having highly reflective or absorptive surfaces for all structural elements beyond the primary mirror itself. And you can also shield the telescope from viewing other parts of the sky that are not relevant, which the telescope James Webb does, because it's using essentially its solar arrays, its huge tennis court sized solar arrays, as a shield against stray radiation from the backside of the telescope. So these things have all been carefully considered with James Webb, and these first deep images tell us that it's a very clean telescope. It has very, very little problem with scattered light.
All right, we just have another minute or two left. One of our participants, Astro Guy, has some questions about the galaxy images, and I'm not sure which of the two images that they're talking about are those galaxies in the same plane. So first, let's pull up the image of the Stephan's quintet, and maybe you can talk a little bit about which of these galaxies are actually interacting with each other, and then we'll switch to the deep field.
So it's a quintet, but once the redshifts were measured, which happened decades ago, it was found that the galaxy to the left in this image is a foreground galaxy. It's much closer than the other four. The other four are essentially at the same redshift, which means they're not exactly in the same plane, because they're obviously in motion dynamically, so they're not exactly at the same distance. And we can't actually use redshift to measure their distance super precisely. But essentially, the galaxy on the left is well foreground of the other four. The other four are in a fairly tight region of space where they're obviously held together by their mutual gravity.
Right, and then in this deep field image, so there's a galaxy cluster in the center, and then there are these curved images of galaxies behind them. Are all these curves from one galaxy, or are there multiple galaxies that are being magnified by the gravitational lensing?
Right.
How does that work?
So that's a good question, so I'll do it in some detail. There are essentially three categories of galaxies in an image like this, in any gravitational lens situation. So sitting concentrated towards the center of the image are the galaxies of the foreground cluster, the cluster at 4.5 billion light years away. And you can see one or two very big, bright, whitish galaxies that are probably defining the center of the cluster. But around them, centered again on the middle of the image, are probably dozens or maybe hundreds of galaxies that are in the cluster. Now, just by looking at them in an image, you can't tell if they're in the cluster. You actually have to measure redshifts, which means you need spectra of all those galaxies. Because to show they're at the same distance, you'd have to show they have the same redshift, and that needs a spectrum. An image won't tell you that. But generically, there are going to be dozens and perhaps hundreds of galaxies concentrated around the center of the image that are in the lensing cluster. Now, also scattered through the image and more easily visible towards the periphery of the image are a lot of other galaxies. You can see they're different colors. I'm not talking about the stretched arcs. I'm just talking about normal galaxies that look round or elliptical or edge-on spiral, or just like randomly oriented galaxies. And those are galaxies at all sorts of different distances, depending on their brightness and colors. They could be 1, 2, 3 billion light years away, and so even closer than that central cluster, or 6, 7, 8, 9 billion light years away, the fainter ones. And again, you'd have to measure redshifts of all of them. But in the general field of this image, there are galaxies at all sorts of different distances. Now, the lens arcs are very particular. They represent a lensing geometry. And so each of those little arcs that you see is indeed reflecting a background, a much, much more distant galaxy than the central cluster, 13 billion light years away, very close to the edge of the universe, seen back in time. Each of those little arcs is the distorted image of a very distant galaxy. And it turns out, though, to answer the question of whether the number of arcs is the same as the number of background galaxies, the answer is not necessarily, because in these lensing geometries you can have situations where you actually get multiple images. And it's typical, actually. You have gravitational lensing, which produces pairs of images. And so if you look carefully at this image, and people at home can do this, you don't have to be an astronomer to do this, you could just print it and measure it yourself. If you see pairs of arcs that are symmetrically distributed on either side of the cluster at the same distance, then they are probably multiple images of the same background galaxy. So that's gravitational lensing producing a pair of images. And if you look carefully and map this image, and astronomers do this all the time, it turns out that there are a lot of those situations. You can have more complex imaging geometries where one background object produces 4 images, or 5, or 7, or 9. It's usually an odd number, just due to general relativity theory. So actually, yes, the number of background galaxies producing these arcs is less than the number of arcs you see, because some of them represent multiple images from the same background galaxy. And you have to model the lensing geometry to figure that out. But people can do that. It's quite a reliable procedure. And that's why it's interesting work, because it's quite complicated to do that rigorously and uniquely. That's a good question to finish with, because it was a complicated one, and it gets into the science of one of the most exciting images. So thank you for joining us, and thanks to Matthew for arranging it so we could see the images too, which made it much easier to talk about them. I'm sure we'll be talking about James Webb in the future, but this was a good day, of course, to highlight what this amazing telescope is starting to show us. So thanks for participating, and we'll be back with you in a few weeks.
Thank you all very much for joining us. Our next Q&A session will be on Twitch in 1 week on next Thursday, the 21st of July. And then we do not have the next one scheduled yet, but we will get those out on our calendar, which you can subscribe to through Google Calendars. I put the link in at the top of the chat. Thank you all again for coming today, and we will see you next week.